Okay, so let's take a look at the first derivative test. First derivative test is used for determining where you have a minimum or a maximum. Let's take a look at our graph. Clearly this is a nice looking cubic. There's a maximum here and a minimum over here. We want to use calculus to find those values. Obviously you could use your TI-83 and graph it and find where it has a max or a min, but the whole idea is to use the techniques of calculus to determine where there are max and mins, and that's what the first derivative test does. So first derivative test, what do? We take the first derivative. So therefore we do f prime of x is 3x squared minus 12x, and then we find the critical values, so therefore we set it equal to 0. So here we take a 3x out, we get x minus 4 equals 0, so x is 0 and x is 4. So we're going to use the first derivative test and the test for increasing and decreasing. So we're using the first derivative test, which really uses the conclusions of the increasing and decreasing test to determine where you have max and mins. So our points are 0 and 4, so therefore we need to determine what the function value is. So f of 0 is equal to 15, and f of 4 is equal to negative 17. Let me fix that. So now my interval, or intervals, are when x is less than 0, x is between 0 and 4, and x is larger than 4. So the next part of my chart is the sine of f prime of x. So we want to use a value to the left of 0, which would be negative 1. So we want to do f prime of negative 1. Between 0 and 4, the easiest value would be 1, so f prime of 1. And a number to the right of 4 would be 5, so f prime of 5. So we plug negative 1 into the derivative, and we get 15, which is positive. We plug 1 in, we get negative 9, which is negative. And we plug 5 in, we get 15, which is positive. So therefore, so our conclusion about f of x is that our function is increasing, decreasing, increasing. So since we know our function is going up here, let me choose another color. Since we know our function is going up, the function is going up here, the function is decreasing here, and then increasing again over here, well, you can see at this point right here, you can see we have a max here, and since it's going down and then going back up, we have a min here. So a lot of times it's helpful for people to draw these arrows, and it's easy to see that there's going to be a max here and a min here because it's increasing, decreasing, then decreasing, then increasing. Again, look at the graph. It's increasing, decreasing, and increasing, so therefore you have a max and a min on this interval. So we want to make our conclusions. First thing we want to write down is when it's increasing, and then where it's decreasing, which is pretty easy. It's between 0 and 4. And then where do we have a relative maximum? Our relative maximum is at 0, 15. And our relative minimum is at 4, negative 17. Again, let's take a look at our graph of the derivative, and maybe that'll help us figure out what's going on here. So here's our derivative, f of x equals 3x squared minus 12x. Here's our original function, f. So here's f, and then here's the derivative. And you notice here the derivative is positive. So since the derivative is positive, my function is increasing. So a positive derivative implies increasing function. In between 0 and I believe 4 it was, the derivative is negative. So that means my function has to be decreasing. So negative derivative gives decreasing function. And then notice that the derivative is positive, so that implies that the function will be increasing all here. Well, since it goes from a increasing function, so a positive first derivative to a negative first derivative means the function changes from increasing to decreasing. So that gives you a maximum value here. And notice that my first derivative changes from being negative to positive, which implies my function changes from decreasing to increasing, which gives us a relative minimum. Let's take a look at another example. Okay, let's look at another example. Here we have a radical function because we have a fractional exponent. Again, just like most things, when we're starting off here, we're going to take the derivative. So f prime of x is equal to 2/3 x to the negative 1/3. We want to rewrite the derivative since it has a negative exponent. I'm going to write it as 2 over 3x to the 1/3. So we want to determine when the derivative is 0. Well, that would be when the numerator is equal to 0, and that's never. So therefore, the derivative never equals 0. But the derivative is undefined when the denominator is equal to 0. And that's pretty straightforward, just getting x is equal to 0. So our only critical value, which is when the derivative is undefined, is at 0. So I'm just going to write out the name of the table here. So first derivative test and tests for increasing and decreasing. So our point is 0, plugging 0 into f. We get f of 0 is negative 4. So our order pair is 0, negative 4. Our interval is only based on 0, so it's to the left of 0 and to the right of 0. We then want to consider the sign of f prime of x. So a value to the left of 0 would be negative 1, and to the right of 0 would be positive 1. So f prime of negative 1 is negative 2/3, which is less than 0, and f prime of 1 is equal to 2/3, which is greater than 0. So therefore our conclusion about f of x is that it's decreasing when x is less than 0 and increasing when x is greater than 0. And so therefore, since it's decreasing here, our function is going down, and then since it's increasing over here, our function is going up. So therefore, in between those two, we're going to have a relative min because the function is going down and then going up. Let's take a look at the graph. You'll notice it's kind of a different looking graph. Again, this is a radical function, that it's decreasing to the left of 0 and increasing to the right of 0. And notice that there's a cusp right here, so it's not differentiable at 0, negative 4. However, it's still considered a minimum because the function is defined at 0. It's just that the derivative is not defined at 0. So therefore, we'll take a look at the derivative in a second. So we have a relative min, and we have a decreasing interval, increasing interval. So let's just write out that answer here. You don't need to watch me do that. So here's our decreasing and increasing intervals. We only have one relative min at 0, negative 4, and there's no relative max. Let's take a look at the graph and the function and the derivative at the same time. So again, here's our function in dark purple, and then in light pink, if you will, is our derivative. So notice to the left of 0, the derivative is negative. All the derivative values are negative, so that means my function is decreasing. So a negative derivative means a decreasing function. A positive derivative means an increasing function. Notice that all my derivative values are above the x-axis, so they're all positive. That means my function is increasing. And then notice that x equals 0, the derivative kind of stops here, and that's just because of the software I'm using. It's implied that this is going up forever and going down forever, so there's a vertical asymptote at x equals 0, because this negative 1/3 can be written down in the denominator. So it's not differentiable at 0, so the derivative doesn't exist. Why is that? Well, because f has a cusp here, or we also know that because by looking at the derivative, there's a vertical asymptote there. So here's a picture of what the graph of the derivative and the function looks like at the same time.